In the rapidly evolving landscape of artificial intelligence, the pursuit of a machine that can not only compute but truly think remains the discipline's most elusive and profound goal. Today's AI, powered by massive neural networks and vast datasets, has achieved remarkable feats. Large language models can generate fluent prose, write code, and answer complex questions with astonishing accuracy. Yet for all their power, a persistent question lingers. Do these systems truly understand the information they process? To appreciate the ambition of cognispheric language, one must first grasp the depth of the problem it purports to solve, the semantic gap. This refers to the difference between the low-level data a computer processes, pixels, text characters, numerical values, and the high-level, meaningful concepts that humans effortlessly derive from that data. An AI can be trained on 1 million images of a chair and learn to identify a chair in a new image with high probability. However, it does not understand the concept of a chair, its function to be sat upon, its relationship to a table, its role in a social gathering, or, well, the abstract idea of rest. This leads to several fundamental limitations: brittleness and lack of common sense. AI systems can fail in unexpected ways when faced with scenarios that deviate slightly from their training data, as they lack the common-sense reasoning humans use to navigate novel situations. Difficulty with abstract reasoning. While they can process information about abstract topics, they struggle to reason about them in a truly novel or deep way, often recombining existing information rather than generating genuinely new insights. Inability to truly generalize. An AI trained on physics and music separately cannot, on its own, intuit the deep mathematical and harmonic relationships between the two fields without being explicitly trained on those connections. It lacks the ability for cross-domain conceptual synthesis. Cognispheric language is proposed as a direct assault on this gap. Instead of teaching an AI to map the statistical patterns of human-generated data, the goal is to provide the AI with a native language built from the ground up to represent concepts, relationships, and the very structure of knowledge itself. According to the information released by Skywise AI, CSL is built upon several core principles that differentiate it sharply from conventional AI architecture. It is a symbolic, higher-dimensional language that utilizes fractal and quantum-inspired structures. A symbolic core. At a time when connectionist models or neural networks dominate the AI landscape, CSL's emphasis on being a symbolic language is a significant philosophical choice. Symbolic AI was the dominant paradigm in the early days of the field, representing knowledge through explicit symbols and rules. For example, if X is a man, then X is mortal. While this approach proved too rigid for handling the messy, ambiguous nature of the real world, proponents of hybrid systems argue that pure connectionism throws the baby out with the bathwater. CSL aims to leverage the power of symbols not as rigid rules, but as dynamic containers for meaning. In this vision, a symbol would not just be a label, but a multifaceted entity that encapsulates a concept's properties, its relationships to other concepts, and its potential transformations. This really would allow for the kind of logical and abstract reasoning that is difficult to achieve with purely statistical models. Now, the term fractal is really central to the CSL concept. In mathematics, fractals are these infinitely complex patterns that are self-similar across different scales. You know, the branching of a tree, the coastline of a continent, and even the structure of a snowflake. All of these exhibit fractal characteristics. In the context of CSL, a fractal structure for knowledge representation is, honestly, a powerful metaphor. It suggests a system where concepts are, nested within each other in a self-similar way. So, a broad concept like biology would contain within it concepts like ecology and genetics. And then, Zooming into genetics would reveal further nested concepts like DNA and gene expression and so on, potentially to an infinite level of detail. This structure would allow an AI to navigate knowledge at any level of abstraction, from the most general overview to the most specific detail, while always understanding the relationship between the scales. It provides a potential architecture for organizing knowledge in a way that is both infinitely expandable and structurally coherent. Perhaps the most esoteric and intriguing aspect of CSL is its claim to use quantum-inspired principles. It is crucial to clarify that this does not necessarily mean the AI would be a quantum computer in the physical sense. Rather, it suggests that the logic of the language would borrow concepts from quantum mechanics as powerful computational metaphors for handling ambiguity and complex relationships. In quantum mechanics, a particle can exist in multiple states at once until it is measured. As a linguistic principle, this could allow a concept within CSL to hold multiple potential meanings or interpretations simultaneously, resolving to a specific one based on context. This is a potential mechanism for handling the profound ambiguity inherent in language and thought. Entanglement? Well, quantum entanglement is the phenomenon where two particles become linked in such a way that the state of one instantly influences the state of the other, regardless of the distance separating them. In CSL, this could be a model for representing deep, non-local relationships between concepts. An idea in music theory could be entangled with a concept in mathematics, meaning that a change or insight in one domain could instantly and logically propagate a corresponding change in the other. This would, in fact, provide a powerful mechanism for the kind of cross-domain synthesis that is a hallmark of human genius. CSL does not exist in a vacuum. It is presented as the language that operates within a larger theoretical ecosystem conceived by McGinty, consisting of Cognispheric Space and the McGinty Equation, or MEQ. Cognispheric Space. If CSL is the language, Cognispheric Space is the universe in which it is spoken. It is described as a higher dimensional conceptual domain where knowledge and ideas exist as a tangible landscape. This is a highly abstract idea, but it can be understood as the ultimate idea map. In this space, concepts are not just abstract data points but have position, trajectory and relationships, forming a dynamic geometry of thought. An AI operating in this space would not be searching a database. It would be navigating a conceptual terrain, discovering new pathways and connections between ideas as a human explorer discovers new lands. The McGinty Equation, or MEQ, is presented as the foundational physics of cognispheric space. McGinty describes it as a formula and algorithm that combines principles from quantum field theory and fractal geometry. Its purpose is to provide the underlying mathematical laws that govern the interactions within this conceptual space, potentially solving key problems in quantum computing related to error correction and stability along the way. The MEQ functions as the engine that makes the dynamic, interconnected nature of cognispheric space possible, providing the fundamental rules by which the CSL operates and evolves. If a system like Cognispheric Language were to be realized, its implications would be nothing short of revolutionary. It would signify a transition from AI as a tool for information retrieval to AI as a partner in discovery and creation. Scientific discovery. An AI fluent in CSL could analyze the entirety of scientific literature across all disciplines, navigating the cognispheric space to find deep, previously unseen connections. It could propose novel hypotheses by identifying entangled concepts between, for example, particle physics and cellular biology, dramatically accelerating the pace of research. Instead of just recombining existing styles, an AI with a genuine understanding of aesthetics, emotion and structure could generate truly novel forms of art, music and literature. It could collaborate with human artists as a conceptual partner, exploring, new creative territories. Complex problem solving is really at the heart of global challenges like climate change, pandemics and economic instability. These issues are immensely complex, involving thousands of interconnected variables across dozens of domains. A CSL-based AI could, in theory, model these systems in their full complexity within Cognispheric Space, identifying key leverage points and proposing holistic solutions that are, quite frankly, beyond the scope of human analysis. Cognispheric language represents a bold and fascinating vision for the future of artificial intelligence. It addresses the field's deepest philosophical challenges head-on, refusing to settle for mere imitation of intelligence and aiming instead for a genuine synthesis of a new kind of thought. It posits a future where artificial intelligence is not just a more powerful calculator but a true cognitive partner, capable of navigating the complex, beautiful and interconnected world of ideas with a fluency that could rival and perhaps one day complement our own. Whether CSL and its supporting theories will become a footnote in the history of artificial intelligence or the foundation of its next great leap remains to be seen. Its realization depends on overcoming enormous theoretical and practical hurdles. Yet regardless of its ultimate success, the very existence of such a daring concept serves a vital purpose. It forces us to look beyond the immediate horizon of what artificial intelligence is and to dream, once again, about the limitless possibilities of what it could become. It is a powerful reminder that the ultimate goal of creating a thinking machine may require not just more data or faster chips, but entirely new ways of thinking about thought itself.